So friends, you have got the basic idea of F-test and the design of experiments. Now it's a high time to start the design of experiment proper. So in that series, the first I will be discussing today about the completely randomized design, that is CRD, which is based on one-way analysis of variance. So let us start the CRD. So in CRD, this CRD is appropriate when the experimental material is homogeneous. So the first criteria for application of CRD is that application material should be heterozygous. And another point you have to note is that it is based on only two principles of design of experiment. So if you remember, there I had discussed in the previous class that there are three principles of design of experiment. The first one was randomization, second one was replication, and third one was local control. So here only two principles we are applying, that is replication and randomization. Why it is called as completely randomized block design? Because of the assignment of experimental unit to the treatment level. Assignment of experimental unit to the treatment level is completely random. So whatever treatment you are applying to experimental material, that process of application is completely random. Each experimental unit is assigned to only one level. So there is only each experimental unit is assigned to only one level. So only one level of replication is you are applying one level of replication you are applying to a particular experimental unit. Now how we are applying the treatments to an experimental unit? Here you see just one example. If there are 5 treatments, say those 5 treatments are A, B, C, D and E, and we have to keep 4 replication for each of these treatments. So each of these treatments you have to apply 4 times. So I hope you might be remembering what is treatment, what are the replications, and what is randomization, which I have already discussed in the last class when I was discussing basics of design of experiment. So 5 treatments, 4 replication for each of these treatments. Then the number of experimental unit we will be requiring will be 20, because there are 5 treatments and each treatment is having 4 replications. So total experimental unit you need to have about 20. And each treatment will be allotted 4 units selected at random. So each treatment, suppose there are A, B, C, D, E, 5 treatments. So each of the treatment you have to repeat it 4 times. That means suppose the treatment A, you have to apply this treatment A in 4 animals. If your experimental material is animal, then in 4 animals you have to repeat the treatment A. Here in the side you can see gain in body weight in pigs under different feed. So what is treatment here? Treatment here is feed. So you are having 5 feeds, F1, F2, F3, F4 and F5, and these are the 20 animals. So that means your replication is 4. So F1 is given randomly, F1 is applied randomly to 4 animals, animal number 1, animal number 2, animal number 3, animal number 4. So what is this 8, 8, 16? These are the measurements after application of treatment, after application of F1. We have taken measurements. What is that measurement? The measurement is gain in body weight. So when you are applying F1 on animal number 1, it is gaining 8 kg. If you are applying it on animal number 2, it is again gaining 8 kg. If it is on animal number 3, that a particular animal is gaining 6 kg, and in 4th animal it is getting 10 kg. So this is how we are applying treatments in case of completely randomized design, that is CRD, and that application is random. We will discuss how we are applying in the latter part of this lecture also. The CRD is basic design, and all other design stems up from this by placing restriction upon the allocation of treatment. So this CRD for any design of experiment, to understand any design of experiment, you have to remember about CRD, because CRD is basic to all, and the way we are placing treatment on the experimental unit, that will be changed in other advanced design of experiments, or we will be putting some restriction how we are placing our treatment on the animals or any experimental unit. So the all thing is depending on the way of placement of treatment or number of replications, and on that basis different type of design of experiments are there. So now this is here you can say a CRD with more than 2 treatment level. So if you are having more than 2 treatment level, can be thought as an extension of t-test of independent samples. So with this you have to remember the t-test for independent sample. If you remember t-test of independent sample, there we were comparing the two different means. Two different means were compared by t-test. But here when you are having more than 2 means, so comparison by t-test will not be possible. At a time, if you want to compare 3 means, it is not possible by t-test, because t-test only compare 2 means at a time. So for that we go for f-test, or that is CRD, or one way ANOVA. So here you can see this is the layout for t-test, layout design for t-test, and this is layout design for CRD. Suppose you are having 20 experimental units, or you are having 20 animals, and these 20 animals are randomly assigned with 2 treatments. In t-test, it is 2 treatments, 2 level of treatments, A1 and A2. So suppose there is 2 feeds, F1 and F2, A1 and A2. Similarly, in CRD, you are having 30 animals or 30 experimental unit, and you are having 3 level of treatments, that is A1, A2, A3. If you are having feed, F1, F2, F3. If you are having any drug, then D1, D2, D3. So this is the basic difference between the layout of t-test and f-test or CRD, completely randomized block design, one way ANOVA. Now when a CRD design has 2 treatment level, already we have discussed it. If a CRD is having only 2 treatment level, then its layout is identical to t-test. So if a CRD is having only 2 treatment, then it is nothing but a t-test. With only 2 treatments, the value of t statistics is equal to f, that is f is equal to t square. So f is equal to t square. If you remember, I have already told you that f test is a variance ratio test and t test is a comparison of mean. So when we are squaring mean, it is being equal to variance. So here f is equal to t square. When 2 means are being compared in CRD, or if you are having only 2 treatments, then f will be equal to t square. If you are squaring the value of t, you will be getting the value of f. So now you see the layout. We will discuss more in detail about the layouts. Suppose you are having t treatment. T treatments means 1, 2, 3, 4, 5 up to t. And each treatment is having R replication. Each treatment, you have to remember it. Each treatment is having R replication. That means treatment number 1 is applied to first animal, second animal, third animal, and up to rth animal. So where with Yij, what is Yij? Being the measurement of experimental unit. Measurement. Yij is measurement. There, if you remember in the last table, I told you 8 kg. What was 8 kg? 8 kg was Yij. That means a particular animal, after getting treatment 1 or any treatment, how it was responding to that treatment is that is called as Yij, being the measurement of an experimental unit belonging to ith treatment and jth replication. Ith treatment and jth replication means treatment 1 and animal number 2 or animal number 5 or treatment 2 animal number 6, anything. Now just let us take one example for understanding the layout of completely randomized design CRD. So number of treatments are 5, A, B, C, D, E, already we have seen. Number of replication for each treatment is 4. Here what I want to discuss with you, that how we are allocating the treatment to experimental units in CRD. So suppose you are having 5 treatment, you may have any number of treatment, 5, 10, 6 or 2 or 3. 2, actually if it is 2 it will be t-test. So 3 from 3 up to n number. So here I have taken 5 treatments, A, B, C, D and E, and number of replication for each treatment is 4. So each of the treatment is replicated 4 times. A, B, 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 C, 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 like that. So total experimental unit, how many experimental units you may be needing? So 5 treatments, 4 replications. So total number of treatment into number of replications. That means 5 into 4 is equal to 20. So you need 20 experimental units. If it is a field experiment, if it is experiment related to fertilizer or any suppose fertilizer, then you need 20 plots, because you have to apply a particular fertilizer into 4 plots, and total you are having 5 fertilizer. In case of animal experiment, you need 20 animals. Each treatment, suppose you have discovered 5 drugs and you want to compare those 5 drugs. So one drug you have to repeat 4 times. That means one drug will be applied to 4 animals. So first of all, we serially number how we are, but suppose you are having 20 animals and you want to apply the treatments, that is drug. So how you will apply? Which animal will get which drug? So for that, first of all, we will serially number the experimental unit from 1 to 20. So you number all the 20 animals from 1 to 20. Then you generate random number. So random number generation I have already discussed many a times. I have discussed in my previous lecture. If you are not remembering, just go and refresh yourself how to generate random number. Even in your Excel, you can generate random number. If you will type in Google how to generate random number, you will get the idea how to generate random number in the Excel. So random number will be generated. Suppose I have generated this random number 0, 4, 18, 2, 14, 3, 7, 13, 1, 6, etc. So likewise this random number I have generated. Now we allot the treatment A to the experimental unit. First four I have allotted experimental treatment A. Then next 4 I have allotted treatment B. Then so on and so forth. So likewise we are applying the treatment to those experimental units. That means you have to keep completely randomized. You have to apply treatments in completely randomized manner. Now just see, this is how I have applied the 4 treatments. So you can see these are the 20 animals and there were 5 treatments. So each treatment has been replicated 4 times and the allotment of treatment is completely random. So now after understanding layout, you might have understood how to put the treatments on experimental material, experimental unit in a random manner. So now we will go for proper CRD, test statistics for CRD. So first of all, you have to see the model. Why model? Because model is telling what is the association, what are the association between the treatment and the measurement that you are taking. That means treatment and observation. What are the factors you want to test and what is the effect of that factor on the particular measurements or observation. So here you can see the model is Yij is equal to mu plus Ti plus Eij. So what is Yij? Yij is the observation of ith treatment. Observation of ith treatment, a particular treatment on jth animal. That means ith treatment on jth animal, jth replication. So Yij is equal to mu. What is mu? Mu is the general mean, overall mean of the observation, of that particular observation, overall mean of the population. Ti is equal to effect due to ith treatment. So particular effect of the treatment. So we are interested to know what is the effect of that particular treatment. And Eij is the error associated with it, because it is not that only a particular treatment is affecting the whole character. A particular treatment is not solely responsible for the a particular observation. Why? Just take an example. Suppose you are giving a feed to a particular animal. So it is not necessary that only feed is responsible for milk yield or weight gain in that particular animal. There may be water intake also, there may be environment also, there may be season also, there may be management condition of farms also. So there are lot many factors, but we are interested to know a effect of a particular factor. So other factors will come under the error. That is why the error component has been discussed here. So Eij is error associated with measurement which is assumed to be normal and independently distributed. Normal distribution. The error is having normal distribution and they are independent to each other. That means there is no dependency between the errors among themselves. So that is why the statistical model in completely randomized design is Yij is equal to mu plus Ti plus Eij. So with this statistical model, we will proceed further. So this is the layout analysis of CRD in one way. So most of the things I have discussed, and you see in first column we have written about the treatment, and second column about the replications, and third column it is total. So if you see row wise, there is T1, T2, T3 or up to TT, the total T treatment you want to test, and this T treatment has been replicated R times, So row wise, if you will see, row wise there are replications R1, R2, R3, Rj up to Rr, and you see Y1 dot. What is Y1 dot? Y1 dot is the observation over the first treatment, over the replications. Suppose 5 animals you have applied treatment 1. So this is the sum of those 5 animals. Observation on sum of the observations of those 5 animals. Likewise for T2, Y2 dot, and this is up to YT dot. That means observation of all the replicants, sum of the observation of all the replicants who have received T treatment. So in one way analysis, this row is having no much meaning, but you will see in the two-way analysis or RBD, when I will be discussing in next class about RBD, then you will see this last row is also important. But here, just to confirm that Y double dot, Y dot dot means grand total. Y dot dot means sum of all the observations. So you can check it whether from both sides this Y dot dot is coming same or not. So this is just for this row is just for confirmation. Now after seeing the layout, now you see how we are actually calculating the statistics. So we notice that each data value, whatever I have discussed, just I have written here in the form of language, we notice that each data value, that is Y11, that means first animal, first treatment, then first treatment, second animal, Y11, Y12, etc. has two superscripts. Two superscripts. So I have already discussed you Y11, there is two superscript. Second one is Y12. So two superscript 1 and 2. What it signifies? The first superscript indicates the row number, that is treatment level. So that is why I have already told you Y11 means first treatment. First treatment, one signifies the first treatment and second one signifies the column number, that is replicate. So first replication. Y12 means first treatment, second replication. The treatment row total are listed across the right hand side of the table. We have already seen the right hand side, this side there was treatment row, total of the treatment or that row sum. Y dot dot is a grand total. We have already discussed it. It is equal to the sum of all the y's and is found by adding the row total. You can get it by adding the column total also. The column total y dot 1, y dot 2, etc. can be used to cross check. This the significance of this column total is just to cross check, but serve no other purpose in one way ANOVA. So already these points I had discussed in the table itself, but here I have kept it in the form of language. Now the actual statistics, how you are calculating. So first of all, in the first step you have to calculate the grand total. So grand total means each and every observation you have to sum it up. So you see y11 plus y12 plus y13 plus y14 up to ytr. What is t? T is the treatment, r is replication. So all the treatments across the replication. So that will be grand total. Here we are writing it in the form of summation yij. Yij means sum of all the observations. So whenever you are getting a problem, you will see one numerical example, then it will be very much clear to you. Now after calculation of grand total, you have to calculate the correction factor. So what is correction factor? So correction factor is equal to grand total square divided by n, total number of observations. So grand total already you have calculated and n you are having. So suppose in case of 5 treatment for replication, so your n will be 20. So grand total square divided by that n, that is 20. Now you have to calculate total sum of a square. For that you need to do square of each and every value. So square of each and every value, yij square. So you do square of each and every value and then sum it up. Square of each and every value, whatever observation you have in that particular table, you square it up and then sum it up and subtract by correction factor. You have to subtract correction factor from that sum of total sum of square. So for getting total sum of square, you have to square each and every value, sum it up, and then you have to subtract correction factor from those summation. Now the next is calculate sum of a square between treatment. That means treatment sum of square due to treatment. So, or this is also called as group sum of square or sample sum of square or between sum of square. Here I have written it BSS, that is between sum of square. So you are having 5 treatments. That means 5 treatment will come in 5 rows. So that is also called as row sum of square. So 5 rows, yi dot. I means first, I means treatment. So yi dot means first treatment, sum of first treatments, means all the observations should be squared and sum of first treatment should be squared and it will be divided by number of observations present in that number of observation means number of observation present in that row, that means treatment, that means replication, that is replication. If you remember that table, whenever you are having doubt, you just go to back to that table and then you will get your answer. I have written in language also, so it will be more clear to you. So y1 dot square divided by ni is the number of replication minus correction factor. So what it is telling, you see, obtain total of all the observation in the group. So in a group you get the total of all the observation. In a group means row, and divide the square of each group. Square, you have to do the squaring of each group and divide it by the total number of observation. total number of observation. Add all these value and subtract the correction factor. So you have to add all these squared value and subtract the correction factor. So you will get like this, you will get between sum of square or treatment sum of a square. Now you are having total sum of a square, you are having treatment sum of a square. So this is the time you will get the residual sum of a square or error sum of a square, and that is also called as within sum of a square. So residual sum of a square is equal to total sum of a square minus treatment sum of a square. So you have got both total sum of a square and treatment sum of a square. So by subtracting treatment sum of a square from total sum of a square, you will get the residual sum of a square or error sum of a square. So with this, the actual calculative step is up to this. Now you have to prepare ANOVA table, analysis of variance table. Why we are preparing table? Just to summarize the result that you have got, because there are many steps in this calculation. So lastly we are presenting it in the form of table, and there you will calculate the variance. You will calculate the variance. We will see in the next slide regarding the table. So what is variance? The mean sum of a square, you will see in the next table, mean sum of a square, MSS, or it is simply mean square between treatment, that is between groups, and within treatment by dividing their respective sum of a square by corresponding degree of freedom. So you will see we are already we are having a sum of a square, and this sum of a square we will divide it by degree of freedom, respective degree of freedom. Then you will get the mean sum of a square, or simply mean square, which is also called as variance. So after getting this mean sum of a square, you have to, that is mean sum of a square is also known as variance. Now since we are doing CRD, completely randomized design, which is based on F test, so you have to calculate F, and you know previously I have told you that F test is also known as variance ratio test. So you have to make the ratio of what? Variance between treatment and variance within treatment. So treatment variance divided by error variance. So treatment mean square divided by error mean square will be equal to F value. So this is how we are calculating the F value. Just last portion from here, these two steps we will see in the ANOVA table in the next slide. So just see. So this is the ANOVA table. So in ANOVA table, these are the very important portion. This ANOVA table you will be asked in your examination, and based on ANOVA table you will get lot of questions either in objective or subjective and numericals. So this is very important. You have to learn how to prepare ANOVA table. So that calculation up to that much, up to error sum of a square you have calculated. Now you have to prepare ANOVA table. So what you have to do, you have to write the source of variation. So what we are doing, we are in F test, we are partitioning the variance. So in a particular experiment, how variation is coming? Your assumption was that you are applying some treatment, and that is why variation is coming. So our aim is that we have to separate the variance. Separate the variance means variance, total variance, you will calculate the total variance, and then you will calculate the treatment variance. Variance due to treatment. And then from total variance, if you are subtracting the treatment variance, you will get the error variance. So that is, so what are the sources of variation? So first source is treatments. So between treatment, what is the variation between treatment? If suppose particular treatment T1, if you are giving T1, what will be the variance? And if you are giving T2, what will be the variance? So you have to find out between treatment variance, and then within treatment variance. In second column, you have to write degree of freedom, DF, degree of freedom. So degree of freedom I have already told you. So this is the number of restrictions that we are applying. So here between the treatments, if treatment is T, we will apply one restriction. So T minus 1 will be the degree of freedom. What will be the freedom? We are applying one restriction, so the freedom will be T minus 1 out of t, we are applying one restriction, though degree of freedom will be t minus 1. And what we are doing simply, for ease of calculation, we are writing here in the last row total variance. So what will be the total degree of freedom? You are having total n observation, you are putting one restriction, so total will be total degree of freedom will be n minus 1. Total degree of freedom will be n minus 1. Now for getting within treatment degree of freedom, what will be the within treatment degree of freedom? It will be n minus 1, that means total minus t minus 1. T minus 1, that is treatment degree of freedom. So if you will solve it, you will get n minus t degree of freedom. N minus t. So within treatment or error or residual source of variation, you will get degree of freedom n minus t. Now in third column, you have to write sum of a square that you have calculated. So sum of a square due to treatment you have already calculated, sum of a square due to residual you have already calculated, and sum of a square due to total, that is also you have calculated. Even if you are calculating sum of a square due to treatment and sum of a square due to total, you will get the sum of a square due to residual. So many times what we used to do, we are giving question in examination and we will just give you between treatment and total treatment degree of freedom, between treatment degree of freedom and total degree of freedom, and I will tell you to calculate within treatment degree of freedom, okay, or error degree of freedom. Similarly, here error sum of a square or residual sum of a square will be missing, so you will have to calculate residual sum of a square. How? By subtracting total sum of a square from or by subtracting treatment sum of square from sum of square due to total. So with this you got the sum of a square. Now you have to calculate the variance which is also known as mean sum of a square or mean square, MSS. So what we will do, we will simply divide sum of a square with respective degree of freedom. So sum of a square due to treatment already you have calculated, and degree of freedom for between treatment it is t minus 1. So sum of square due to treatment divided by degree of freedom t minus 1 is equal, it is mean sum of square due to treatment. Similarly, for error mean sum of square, that is error variance, it will be sum of square due to error, that is residual, divided by degree of freedom of error. So this is called as mean sum of square due to residual. So this mean sum of square are variance. Actually these are the variance. So that is why we are just taking the ratio of these two variance and we are calculating f value. So f value is the ratio mean sum of square due to treatment and mean sum of square due to error. So this is how we are calculating ANOVA table. This ANOVA table preparation is very crucial in any of the design of experiment. So with this we got the f value. Now you have to interpret your result, because you have got the f value, you have to interpret your result. So just see the ANOVA table. This ANOVA table is always one-tailed, and that too right-tailed. Means critical region will be available in right hand side. So why it is one-tailed, that you have to find out. So this is your assignment. You have to find out why ANOVA test is always one-tailed, because their rejection result will be on the right side only. Now what if you have calculated the f value? You are having two hypotheses, H0 and HA. H0 null hypothesis and alternate hypothesis. What was null hypothesis? Null hypothesis was that all the treatments that you are applying all the treatments that you are applying are equal, and alternate hypothesis was that they are not equal. So if your calculated value is less than the critical value of f table, so you have to consult f table, and from f table you have to get the value. But here seeing value from f table is having one special thing that you have to remember. The critical value of f you are seeing at treatment degree of freedom and error degree of freedom. Treatment degree of freedom V1 and error degree of freedom V2 at 1% or 5% level of significance. So till now in t-test what we are doing, we are seeing just 1 degree of, at 1 degree of freedom we are seeing the table value of t. But here the F test, in F test, because this is the variance ratio test, so that is why there will be involvement of 2 degree of freedom, 1 degree of freedom for treatment and another for the error. Treatment and error degree of freedom, that means numerator and denominator degree of freedom. If you remember the formula, so this is numerator degree of freedom, this is numerator, here numerator and denominator. Numerator it was treatment and denominator it was error. So treatment degree of freedom and error degree of freedom. How to see table, just I will tell you how to see the table. So and vice versa, if your calculated value is greater, then you will reject the null hypothesis and accept alternate hypothesis, as we are doing earlier also. So just see this table, F table. This is the V1. That means treatment degree of freedom. This side you have to see the treatment degree of freedom, and this side you have to see the denominator, that is error degree of freedom. Treatment degree of freedom and error degree of freedom. Here you see the treatment, this line I have marked the value 3.06. Here the degree of freedom is 4 because you have taken the 5 treatment. So degree of freedom will be 4, 5 minus 1, 4. And error degree of freedom, this side, this side, this side. So 5 into, and your replication was 4. Your replication was 4. So total degree of freedom for error, it will be coming 15. So at 4 degree of freedom for treatment and 15 degree of freedom for treatment, the value is 3.06. So this here, whatever you are getting F value, calculated F value, if it is greater than tabulated value, then you have to reject null hypothesis. If it is lower than tabulated value, you have to accept the null hypothesis. Now, very quickly we will see one example. So there are 5 varieties of feeds equally and randomly allotted to 20 pigs. So you are having 5 feed and 20 pigs. So this is the observation that we have got. So this table I have already shown you in the earlier also. So these are the gain in weight after taking feed 1, feed 2, feed 3, feed 4, feed 5. So 5 treatment and 20 animals. Each treatment has been replicated 4 times. Each treatment has been replicated 4 times. So F1, 1, 2, 3, 4. F2, 1, 2, 3, 4. So these are the treatments and these are the replication. So here you have to analyze the data for comparison of feed. So you cannot do it by t-test, because in t-test only 2 treatment mean can be compared. But here you are having 5 treatments. So how you will go? You will have to do ANOVA. So just see what I have done. I have find the total F1 total. F1 total means all the treatments on the right hand side. This is just see, if you go back this side, this side. So 10 plus 6, 16, 8, 24, 8, 32. So here 32. Similarly 10 plus 12, 22, 3, 25, 35 or 9, 35, 9, 44. So likewise we got the F1, F2, F3, sum of these all treatments. So here this is the value, sum of all the treatments, F1, F2, F3, F4, F5, and this is the grand total, all the sum of all the observations, and these are the mean of the feed 1. So mean of the feed 1 means you are adding all the feeds, you are already adding all the feeds and you are taking mean of all the feeds divided by total number of feeds, sum of the feeds and divided by total number of feeds. So likewise you calculated the total and mean of each feeds. Now you have to just before that you have to state the hypothesis. So our null hypothesis, feed do not differ from each other, and alternate hypothesis, at least two feed differs from each other. So alternate hypothesis, at least two feeds are differing from each other. So you have found the grand total 224, total number of observation was 20. Now with this you find the correction factor. So correction factor is grand total square divided by total number of observation. So grand total was 224, 224 square divided by 20, you are getting grand total as 2508.8. Now similarly you have to calculate the total sum of square. So what is total sum of square? So each observation should be square and added. Each observation should be squared and added, and it will be subtracted by correction factor. So 8 square plus 10 square up to last value, that is 8 square minus correction factor. So you will get the total sum of square as 207.8. Similarly, you have to find the feed sum of square or treatment sum. Here treatment is feed, that is why we have written treatment sum, feed sum of square. So what was feed sum of square? Sum of first feed. So what was sum of first feed? You remember it was 32. So 32 square plus 44 square. Actually it is 32 square by 4 because replication 4. N is 4. Then 44 square by 4, 64 square by 4, 48 square by 4, 36 square by 4. So here the replications are equal. There are equal replication 4. So that is why instead of writing separate 4, 4, 4, I have written here 4 commonly. So I think you understand it. So if your replications are different for different treatment, then you have to vary the n also. So then in that case you have to write it separately. Suppose the first treatment is 3 times replicated 3 times, so 32 square by 3. Second treatment 5 times, 44 square by 5. So likewise you have to proceed. So feed sum of square, that is treatment sum of square, you have obtained 155.2. Then after getting total sum of square and feed sum of square, you have to calculate the error sum of square. So how you will calculate error sum of square? Total sum of square minus feed sum of square. So this is coming 52. So till now you have calculated all the sum of squares, total sum of square, treatment sum of square and error sum of square. Now you have to prepare the ANOVA table. So with this actual example you have to prepare the ANOVA table. Just remember how we were preparing ANOVA table. So for ANOVA table you have to prepare different columns. First column, source of variation. Source of variation, what will be the source of variation? So between feed source of variation, then error source of variation, that is within feed, and total source of variation, total variation. If you see the column, then column degree of freedom, second column, then sum of square, mean sum of square, F value, and these are the value of from table that I have kept here, value obtained from the table. So just see the degree of freedom between feed. So total feeds were 5. So 5 minus 1 is equal to 4. Then total there were 20 observations. So 20 minus 1, 19. And if you are subtracting 19 minus 4, that is total minus feed degree of freedom, you will get the error degree of freedom, that is 15. Similarly, sum of square you have already calculated 155.2 for treatment sum of square, that is feed sum of square, and total sum of square you have calculated, that is 207.2. You subtract 207.2 minus 155.2, you will get 52. So like that you obtained the sum of square. Now you have to calculate mean sum of square. How you will get mean sum of square? Mean sum of square will be mean sum of square due to treatment, that is feed, it will be 155.2 divided by its degree of freedom. What was degree of freedom? It was 4. So if you will divide it, you will get 38.8. Similarly, you will get mean sum of square due to error. So how you will get error? 52 divided by total number of degree of freedom. 52 divided by 15. It will be 3.47. And then F value. F value means the ratio of two variance. Variance due to treatment divided by variance due to error. So variance due to treatment is 38.8 divided by 3.47. 3.47. So if it is 3.47, and if you will calculate, you will get the table value, calculated value of F as 11.18. So this is the calculated value of F. Now you have to consult the F table. So if you are consulting F table, at what degree of freedom? So numerator degree of freedom was 4. So if you will have to go to 4 degree of freedom, and then denominator was 15. So 4 and 15. So this 4 and 15, the value is 3.06. You will see the table and then you will get the value of F at 5% degree of freedom, 3.06. So this 3.06 is calculated value is greater than tabulated value. So what we will do here? We will reject the null hypothesis. We will reject null hypothesis, because our value is 11.18, whereas tabulated value is 3.06 at 5%, and 1% also it is 4.89. So here we will reject the null hypothesis and accept the alternate hypothesis. That means, what was our alternate hypothesis? That any of the two feeds are different. But which two feeds are different? For that, we have to do some other statistics also. Here, till now, if your F value is significant, you got an idea that means are different. But which means are different? Which two feeds are different? Or which three feeds are different? That you have to see. Either F1, F2 are different, or F1, F3 are different, or F2, F3 are different, F3, F4 are different. Which one is different? For that, we have to go for calculation of critical difference, CD value. So that I will be discussing in the next lecture. So this is about the calculation of F test in one-way ANOVA or completely randomized design, CRD. Now, just for academic purpose, sometime in your examination, they may ask, question may be asked, what is the advantages or what are the merits of CRD? So after seeing all this, you can now answer what are the advantages or merits of CRD. CRD is actually simple, very simple. Layout is very simple. Just you have to remember that you have to randomize the treatment. That is the only motto of CRD. It is most flexible design. Why it is most flexible design? Because any number of treatment and any number of replication can be used. So there is no restriction for number of treatment and number of replication. Statistical analysis of this design is very simple, even in case of unequal number of replication. If you are having unequal number of replication, as I was discussing in between the calculation portion, that if you are having even unequal number of replication, then also you can do the analysis. It is also applicable for missing observation. Even if few values are missing, then also you can do the statistical analysis in CRD. But that is not under our purview, so we will just ignore this one. CRD provide maximum number of degree of freedom. So we will see why CRD is providing maximum number of degree of freedom. Because there is one restriction. There is only one restriction. Which restriction? That is the number of treatment. So if there is only one factor that you want to know, that is treatment, then you will get maximum degree of freedom in comparison to other design. So if you will see, we will discuss another design, then you will remember that, or you will realize that how CRD is giving maximum degree of freedom. Now, what are the demerits or disadvantages? So there is no local control in CRD. So if there is no local control, if you remember the design of experiment principles, the third principle was local control. If there is no local control, that means you must have the homogeneous experimental unit. Experimental unit should be homogeneous. If it is heterogeneous, you have to apply the third principle, that is local control. So for CRD, you need homogeneous experimental material. And another thing that is emanating from the first one only, that here experimental unit are, you are not applying any local control. That is why there is chance that experimental unit will not be homogeneous, and there is chance of experimental error. The third one is CRD is not suitable for field experiment. Why? Why it is not suitable for field experiment? Because in field you will get different kind of experimental unit. The homogeneity of experimental unit in field is very difficult. That is why it is not suitable for field experiment. The fourth one, as the number of treatment increases, experimental error increases because heterogeneity increases. So that is also, all the demerits are based on only one thing, that your experimental material is, if heterogeneous, then there will be error in case of CRD. So with this, I have discussed the various aspects of completely randomized design, that is based on one-way ANOVA. In next class, actually, I will be discussing about the critical difference value, how we are calculating the critical difference value, and then in another class, I will be discussing the two-way ANOVA or RBD, that is randomized block design, how this randomized block design we are calculating the statistic for RBD. So with this, thank you. We have come to the end of the lecture. Thanks.